Alright, good morning, and here we are again for the final part of this lecture, part 3 for MENG 3310, fluid mechanics. So this is again this lecture, of course, has been divided into 3 pieces and filmed over a longer period of time than I would normally hold a lecture, but that's fine. We'll still get everything up on the site within a reasonable amount of time. Okay, so right now I'm going to record the third portion of the lecture, and this is let's see, again, today is September 6th, 2016. It's about 10 a.m. and we have enough time to get through this. So I have a third section, which should hopefully be a bit shorter. And I'm going to go through the derivation for the equations for calculating forces on flat submerged bodies or flat submerged surfaces. So this is section 2.8 and 2.9 in the text, and I have a few lesson objectives. First, I wish to determine the magnitude and direction and location of hydrostatic forces on submerged flat surfaces. 2, solve rigid body statics problems involving hydrostatic forces on submerged flat surfaces. And 3, explain the difference between centroid and center pressure. So I'm going to go over 2.8 and 2.9. 2.9, I believe, does talk a bit about the prism method, which is another useful thing that I don't think we're going to have quite time to get through. And in similar vein, the 2.10, I believe, is covering curved surfaces. I will cover both prisms, pressure prisms, and curved surfaces when I'm teaching this course for civil engineering students, MENG 3310. But the mechanical engineering course has slightly different material. There's material that we cover in mechanical that we don't cover in civil. So in working in civil, we have a bit more time to work on some of the more advanced applications of forces on submerged surfaces. So anyway, I'd rather just focus on calculating forces on simple systems of plane surfaces. So let's begin. So I'm going to attempt to draw a rather elaborate diagram, relatively elaborate diagram, and hopefully I won't screw this up too badly. So let us discuss hydrostatic force on a plane surface. And I am going to derive this for an arbitrary plane surface. Think about a metal plate or something like that of any arbitrary shape. Well, any flat shape. Well, I guess a plate would, by definition, be a flat shape. But we can have a plate or a shape of really any form. So I'm going to kind of draw it like a potato, like I do in, say, when I'm teaching statics. So on a plane surface, so first thing I'm going to have is I'm going to have the free surface of the fluid. And that would be my 0 elevation here. So I have a free surface here. This is all going to be done in terms of gauge pressure. So this is the free surface. Now, I'm going to extend a line down at a certain angle. And this angle is going to be theta. Okay, this is going to be theta. And then I'm actually going to draw the object or the surface that I'm considering. So from the side, it's just going to look like a plate, but I'm going to project this down to illustrate that this is an arbitrary shape. So this is looking at it from the side, and then I'll show what it looks like from the front on, from the front essentially. Okay, so let's do that. First of all, I'm going to draw some projection lines. Well, actually, the first thing I'm going to do is draw some axes. I'm going to have a local x-axis, which is here. This is going to be my local x-axis. I'm going to use an x and a y-axis that are, my y-axis, my local y-axis is going to be parallel to the plate, and my local x-axis is going to be perpendicular to the plate. So this is the local y-axis that I'm using for all of this. Alright, moving on. Then I need some projection lines. I think I'll do my projection lines in yellow because those don't, I don't really want them to show up too well. They're just really to help me draw this, if not accurately, at least kind of semi-neat. It's easier to draw this on a piece of paper where you can use a straight edge, but if I'm using a tablet, obviously I can't as readily do that. Well, now there are some tools I could use, but anyway. So now I'm going to draw what this thing looks like from the front. So it could be any arbitrary shape, just really any arbitrary kind of potato type shape. Doesn't really matter. And then this potato is going to have a certain centroid. This plate, this arbitrary shape, is going to have a certain centroid. So this here is going to be my centroid. It's going to be my centroid, and the centroid fundamentally is the actual the centroid of the actual shape. So this is the centroid of the actual surface itself. Now pressure will have a different centroid. The reason pressure has a different center than the shape itself does is because pressure increases with depth. Okay, and now I'm going to label a few dimensions in relation to this centroid that I will need to use. Let's see. So I'm going to say, let's say, okay. Well, first of all, I'm going to have a YC, or sorry, actually this is going to be an XC. XC is going to be the X coordinate of the centroid, and my YC is going to be the Y coordinate of my centroid. YC is going to be the Y coordinate of my centroid. So again, this is X and Y, so this is YC, the Y coordinate of my centroid. Then at some other place, usually at a lower depth, I'm going to have a location that I call the center of pressure. This is going to clearly, I'm actually trying to draw this, I'll actually draw it, make it clear that it's at a different X value as well. I don't like how that looks, let me just call it X there. Okay, so this point here is going to be the center of pressure. This point here is the center of pressure. And then this has a few coordinates that we'll need to keep in mind. I'm going to say, okay, well this has, I'm going to use a subscript R for the center of pressure because that comes from the word resultant. This is going to be XR. The X coordinate of the center of pressure, or the X coordinate of the resultant. This is going to be the force. If you do a vector sum of all the pressure forces acting on this surface, this is going to be where that equivalent force acts through. And then I'm going to need a YC as well. A YC here as well. Or sorry, a YR. YR is going to be the Y coordinate of the center of pressure. Then let's see, I'm going to also say, I'm also going to keep in mind what I call the HC, which is going to be the depth of the centroid. And that will depend on the geometry and on theta. I'm going to have HC. HC again is the Y coordinate, not that I shouldn't say the Y coordinate, sorry, the Y coordinate is along this axis. HC is the height or the depth directly under the surface of the water of the centroid of the shape. Now I need to define one other thing. We're going to be doing integration here, and I need a dA. I like to use red for my dAs, so I'm going to do that. I'm going to show dA. This is dA, and it's my little elements of integration. This is dA, and it has a corresponding piece on the plate itself. This is going to be dF, little tiny arrow dF. So at any given depth and any given location on the surface of the plate, I'm going to have a dA, and depending on the depth, this is going to have a certain dF associated with it. And then acting through this point here, acting through the center of pressure, I'm going to have a much larger arrow, and this is F sub r. This is the overall resulting force of all the pressure acting on the plate. So again, this is an arbitrary plane from a free surface, and depth varies across the surface. Okay. So that should do it for my nice messy diagram. Now we have a few things I want to discuss. So let's start working through this. You can determine the force acting on dA as well, dA as dF is equal to gamma h gamma times h dA. So to get the force, all we really do is multiply by the pressure. So this is here, this of course gamma times h, this is your pressure. Moving on, if I want to find the total force, say I want to find the total force. Okay, so the total force, or magnitude, resultant, whatever you want to call it, will be the surface integral of this. We simply integrate over the surface. Integrate over surface. Integrate over surface. So FR is equal to the integral of dF is equal to the area integral of gamma h dA. So I'm just going to take this and integrate it. I just add an integral to both sides, and I get this, the area integral. And then I can say, all right, well, this is the area integral of, I can replace h. Okay, well, I'm going to realize a certain geometric relationship here, and that is my simple, trigonometry. I have theta, h, and y here. So my relationship is y sine theta equals h. Y sine theta is equal to h. So I'm going to replace h with y sine theta. So I can say integral of gamma times y sine theta dA. Now, we did look at a case yesterday, or earlier in this second lesson, where gamma wasn't constant. But if gamma is constant, as it is in most cases with our fluids, so you can do something else. If gamma and theta are constant, then we can pull out this gamma because it's not going to be varying if the fluid is incompressible, in other words. So FR then is going to be equal to y sine theta, y sine of theta times the area integral of y dA. This should look familiar. The area integral of y dA. This should pop out at you as something you saw in statics class. Some of you should definitely know because I taught it to you in statics class. This is the first moment of area with respect to the x-axis. This is the first moment of area with respect to the x-axis. So if we recall from statics class, so let's do a bit of review for those who've forgotten what I taught you. I know, it's summer's long and forgetful. If you recall from statics, well, let's see. And I guess yeah, you all had dynamics between statics and here, so yeah, I guess you can forget some of this stuff, but such is life. So let's do a bit of a review. If you have an arbitrary plane shape here, just like this, and you have a dA, again, dA being the element of integration, not the district attorney. I hope you don't have much contact with the dA. But anyway, that's neither here nor there. If you have this dA with coordinates on the plane xy, x measured from the y-axis. Oh, well, I can't draw a line, can I? X and y. Then we have we have two first moments of area. The first moment of area. Moment of area with respect to x-axis. I'll put, dang it, looks really bad. I'll come back and write it. And the first moment of area with respect to y-axis. And what do these equal? Let's write the formulas. This is going to be equal to the area integral of y dA, which is in turn then equal to y CA, the y coordinate of the centroid times the area. And then with respect to the y-axis, it's the area integral of x dA, which is then equal to the x coordinate of the centroid times A. So then, I can say then, let's see, I go back to what I had previously here. FR, wow, looks so bad. FR equals gamma sine theta YC A, which is then equal to gamma A. Let me pull out the gamma A. Gamma A times YC sine theta. So in other words, what I've done is I have taken the, I replaced this integral here with this expression here. And I can also realize that this gamma c or yc sine theta, this is just hc, the height or the depth of the centroid. Hc is depth of centroid or height of centroid. We'll just say depth of centroid of area below free surface. Below the free surface of the fluid. Below the free surface. Oh, and we seem to be losing something here on PowerPoint. Uh-oh. Thankfully, oh. And my thing just crashed. Lovely. Well, thankfully it's still recording. Let's see if this will... Nope. Well, I don't like it when that happens. I had having some technical difficulties, but thankfully the camera is still rolling, so we didn't lose anything. At least in terms of the video. Alright, so let me just review. Man, I hate it when that happens. Doesn't happen that often, but to err is computer, I guess. So FR is gamma sine theta YC times A equals gamma A times YC sine theta, and again this is equal to HC. This is equal to our HC, the depth of the centroid. However, if I then go and simplify this, I can get the final result that I'm really looking for in terms of the magnitude of FR, and that is that FR is equal to gamma HC times A. FR is equal to gamma HC times A. Notice, this is not dependent on theta. It doesn't actually matter what the theta is. All you'll need to do is to find the area of the shape and the and the depth of its centroid, and you can find the equivalent force on this thing. So again, this is the resultant force of a pressure distribution. Of hydrostatic pressure on a flat surface. On flat surface. Okay. Now, another way to say this is we can say that resultant force equals the pressure acting at centroid of area. Or depends on, pressure acting at centroid of area, times the total area, times total area. That's another way to conceptualize this. Times the total area. So the question then becomes, now that we have its magnitude, the next question becomes, where does it act? So we've found the, now if I could, I'd go back and highlight some things in the diagram, but thankfully it's still in the video, I hope. We have found the magnitude of the resultant, but we need to figure out where it acts. And it's very tempting to say, oh, it acts at the centroid. Derp, obviously it just acts at the centroid. Well, that's not true. It does, the force acts through its own center, the center of pressure. So we'll need to find out how to calculate YR, the coordinate of the center of pressure. So we need to find YR, the Y coordinate of resultant. I need to find where along the y-axis that the center of pressure, or the resultant of pressure, will be acting. And the way we're going to do this is simply using balance of moments. We're going to sum moments about or around the x-axis, and the moment of the resultant must equal the moment of the distributed force. As long as we believe in statics, as long as we still fear the ghost of Newton, this should be possible. I love that phrase. It's one of the more colorful phrases I use in my lectures sometimes. As long as we still fear the ghost of Newton. Anyway, I just love the juxtaposition of putting a superstitious idea next to something highly scientific. It's wonderful. Anyway, well, that has nothing to do with fluid mechanics. So FR, YR. We're after YR, the y coordinate of the center of pressure. And this is going to be equal to the integral of the area integral of y df. So we're going to integrate the force across, and this is then equal to the area integral of y gamma h dA. Here I'm just turning the y into a, well, not necessarily, I'm just applying the integral. And this is then equal to the integral of y gamma times replacing the h with y sine theta dA, and then this is equal to the integral of y squared gamma times sine of theta dA. Now, since FR, that we knew previously, the previous derivation of the resultant, is equal to gamma times yc sine theta, times A, I can then plug this into here. So I'm going to get that, I'm going to have gamma yc sine theta, and that's in parentheses, times A times yr, again I'm substituting this expression into here, and then I have it equal to this one here, is equal, as long as our theta and our gamma are constant, I can pull them out, gamma sine theta times the integral of y squared dA, and then if I go and cancel some, now I can start canceling a few things out to simplify things. I can't decide which side it wants to be on. Actually, no, sorry, I don't get rid of that. That stays around. I do get rid of the gamma and the sine theta. Gamma and sine theta. And so then I am left with, and then a miracle happens, YCA YR is equal to the integral, the area integral of y squared dA, the area integral of y squared dA. And this is kind of important. This is another thing that should pop out at you from statics. This here, the area integral of y squared dA, is the moment of inertia about x, moment of inertia about x, or the second moment of area, ix. Two names for the same thing. Second moment of area ix. Now, if we recall from statics, if I have a potato and I have a y and an x-axis, actually let me just draw this like this. If this is my x-axis, then my little dA, and then a certain distance y from the x-axis here. So Ixx is going to be the integral of y squared dA. And I know I drew the x-axis vertically. You could flip it around the other way if you wanted to. Ixx is also equal to the integral of y times y dA. Another way to conceptualize this. So again, this is with respect to axis formed, and this is going to be our x-axis again is going to be x-axis from previously, from the original diagram, with respect to axis formed by plane containing surface and free surface. I'm going to say the plane containing surface and free surface, or at least their intersections. Really, you just need to think of it as the moment of inertia of the flat shape. For example, if you were to use a rectangle, the common rectangle, you'll remember a simple rectangular shape has a moment of inertia. Well, if this is, say, B, and this is A, and this is our x-axis, and this is our y-axis, well then Ixx is equal to 1/12 AB cubed, and Iyy is equal to 1/12 A cubed B. Now, however, but Ix is in, so we do need to consider something though. Ix is in relation to the global x-axis. We need something compared to the local, really, because that's what we really want to find. But Ix, or we need to get it into the, it's in the local right now, but anyway. we need our Ix in our formula to be in relation to the global, not the local. But Ix is in relation, so our Ix in our formula here is in relation to the global, not the local. Is in relation to global x-axis. I know this can be a little confusing, but it'll all come together in the final formula, thankfully. And to do this, we'll use our old friend, the parallel axis theorem. And so Ix is then equal to Ixc plus a yc squared. And really, or we can say here, this y, that's fine, Ixc, and then solving around, we could get, transforming this, I can get my final resultant. Yr is simply equal to Ixc over yc times a plus yc. And here yc is going to be the distance to centroid of area from the top of our plate, or from the surface along that angle, along our local axis. Again, please do not confuse. I don't know how many times I need to mention this, but I know I'm repeating myself, but it's kind of important. Do not confuse y and h. Do not confuse the centroid of area with the center of pressure. Yc is distance to centroid of area. So our center of pressure, our yr, is actually going to depend on our yc, and the Ixc is the second moment of area with respect to the second moment of area with respect to x. Second moment of area with respect to x about the centroid of the area. So this depends only on the plate's geometry and the depth, I guess. About centroid of area. And then we can move along and do something similar for xr. Can do same for xr. And we can say fr xr equals the area integral of y times sine of theta gamma x dA. And then xr is going to be equal to, plugging in fr and sorting around, the area integral of y sine theta gamma, let's see, well actually let me say, if I divide by xr, let me solve this a little differently. Xr is equal to the area integral of xy dA over, I can just cut a few steps out and say, over yc a, which is equal to ixy over yca. Yc times a, ixy is one quantity. This is not I times x times y, these are subscripts. So xr then can simply be said to be ixy, let me call this ixyc, and I'll define what this is. And this is applying my parallel axis theorem, etc. Ixy is the product of inertia with respect to x and y axis. It's combined. With respect to x and y axis. And our final formula then for the x coordinate of this is going to be Ixyc over yc times a plus xc. And let me put a box around that. And xc is the x distance to center of area, or to centroid of area. xr is the x coordinate to the center of pressure, to center of area. And ixyc is product of inertia with respect to x and y, about the area centroid. If you do not know the difference between with respect to and about in this context, please review your statics textbook. About the with respect to x and y, about the area's centroid. So then, finally, if you want to get we do have a nice table in the book that can help summarize some of these things in terms of finding the IXY, the moment of inertia, things like that. See figure 2.18 for common shapes. For XY, for IX, IY, IXY, XC, and YC. All right, and then I think that'll do it for today. So that's the end of lecture. That's the end of the third part of this lesson number 2. I know it's been quite a ride today and yesterday, but we finally got it done. So that should do it for now. If you have any questions, feel free to stop by my office hours or see me. There will be a second assignment that I'll be posting to the website shortly. I will see you all next Monday for an in-person session as normal, and as always, thank you.